This is Module 2, Where Does Bottled Water Come From? Lesson 1, How can the scientific method be used to assess water quality? In this lesson, we will be talking about the scientific method. Now, this is something that everyone should have been introduced to when they were younger, right? So you ask a question, you form hypotheses, you come up with a methodology, you execute it, you get some results, you analyze, and then you make some conclusions. And it's important to understand the scientific method because you can basically use it to test anything. It's not only hard science that we can use it for, it can be used for in your everyday life. And it is to determine the validity of scientific claims. In this lesson, we will be using an example from your book, which occurred in 2006. Fiji, the water bottle company, ran full ads in several magazines and TVs that said in the title, the label says Fiji because it's not bottled in Cleveland. Now, it's basically implying that the advantage of bottled water, particularly from Fiji, is that it would be better, right, than Cleveland water. But how do you know whether this claim that all Fiji water is better than Ohio water is scientifically valid? Well, that is what we're going to go into. So here the overarching purpose is to understand whether bottled and tap water are very different and if the quality is better. And you test that through answering questions. First, coming up with a question, right? That is both testable and falsifiable. This is the first step. And here you can see several questions that can be asked in each of your book's units, and some that are not testable, right? So for this one, can microplastics be detected in the blood of humans? And a non-testable question is, should microplastics production be banned? Because that is based more on opinion and bias. These are the steps in a scientific method, right? This is a very simple methodology. Make an observation, ask a question, develop a hypothesis, which is a testable statement that must be falsifiable. Test the hypotheses, determine if results support the hypotheses or show the hypothesis to be false, and if necessary, develop a new hypothesis based on results and start the process all over. So back to our original instance, which was the Fiji water ad. They're basically claiming that bottled water is better than tap water. So what would be the question here? Well, it would be, are there differences in the contents of bottled water versus tap water? Not, is bottled water better than tap water? And that's because at the end of the day, when you employ the scientific method, you need measurable variables, aka testable variables, and then you can make, inferences, conclusions, if it comes out that those variables are leaning towards something, right? The hypothesis is that tap water contains high level of chemical contaminants when compared to bottled water. Now, hypotheses can be tested using both observational and experimental studies. Observational studies just involve observations of subjects. This is what we see related to human and animal behavior. and a lot of ecological natural ecosystems studies are observational because they cannot be recreated in a lab. Experimental studies involve the direct control of variables, meaning you can manipulate things, correct? Usually there's an independent variable, which is something that is intentionally changed in the experiment, and a dependent variable, which results from the changes to the independent variable. In other words, during an experiment, the dependent variable is determined by the independent variable. Now, what are controlled variables? If you notice here that this is a scientist who's taking a water sample and he's wearing PPE, personal protective equipment, to prevent the sample being from contaminated. And that's one way we can control variables in an experiment, because on our bodies we carry bacteria, we carry elements that could fall into that test tube that he's holding and contaminate it. So I actually worked at Turkey Point Nuclear Generating Station. There is a mitigation wetland surrounding the power plant, and due to state and federal regulations, water needs to be tested in that wetland constantly, because to actually cool down the giant, massive nuclear generators, they have to run high levels of salted water. The salted water retains like the cooling effect of water much easier than non-salted water. And so those high levels of salts need to be then released into the environment, and that could cause a problem. Since this was such a sensitive subject, the water quality around Turkey Point, I did have to wear PPE. Not exactly like this, but I had to have my hair tied up. I had field clothes that were specifically designed to make sure that nothing on my person would contaminate the water samples I was taking. And several experiments, particularly clinical trials with humans on new pharmaceutical products or treatments, will have a control group, which will receive a placebo, which is a substance that is identical to what the experimental group receives, except that it does not include the active ingredients. So the basically the control group does not receive the active treatment, right? It might be a little bit different. Nope, sorry. And this is used as a basis for comparison in the analysis of results from an experiment. So let's go back to our bottled versus tap water experiment. Our hypothesis right now is that tap water has higher amounts of contaminants compared to bottled water. Now, an observational study would not work for this, because the hypothesis is asking for chemical contaminants, which are usually invisible to the human eye. So we need to do an experimental study, which requires us to design and then identify the independent variable, which will be the type of water. Now, what is one common type of contaminant? Well, we have mercury. In this case, we're looking at arsenic, and that's because it's a naturally occurring chemical found in drinking water and that are sourced from groundwater aquifers. And the long-term exposure can lead to the development of cancer and heart disease. So, in the experiment, the independent variable would be the actual type of water, whether it's bottled or tap. And then the dependent variable would be the amount of arsenic, which would depend, right, on the independent variable, which is the type of water. So I hope this kind of starts making sense. Because if you get some results and you plot them on an x and a y axis, the x-axis will be the type of water, and then the y-axis, which is the dependent variable, would be the the type of the amount of arsenic. So that changes based on the type of water, which is the independent variable. Now, this is very, very important. When you actually test things, you want to have more than one sample of each one. Higher numbers of samples in an experiment will decrease the impact of uncontrolled variables. And to control additional variables in the experiment, you can take the same number of samples, test the same volume of water from each, store the samples at the same temperature, and use the same equipment to test them for arsenic so that there is nothing that is changed, right? And to ensure that results are accurate, you can also include a positive and a negative control. A positive control will be water with arsenic intentionally added at a specific amount, right? Something that you can compare it to. And a negative control is pure water that has no arsenic, right? So for both of these, you know the exact levels. One has none, one has a specifically added amount. And then after we conduct the experiment to test the arsenic levels, you analyze and determine whether you support or reject the hypothesis. So to put it all together, because I know that's a lot of stuff, this is the example simply laid out. Keep this in mind. It's very actually easy. I know I talked a lot and it might seem more complicated, but overall, this is what our example is. And obviously, the hypothesis is that there are more contaminants in tap water than bottled water. So this actually did happen, right? The city's public utilities director had both the Fiji water and the city tap water tested for levels of arsenic. And what they found is that the Fiji water contained more than 6 micrograms of arsenic per liter, while the Cleveland tap water had none. Okay. So, with regards to arsenic, our original hypotheses would not be supported by the data. The arsenic level measured in Fiji water was still below the EPA limit, which is set at 10 micrograms per liter, but the results may be different from what we have expected. Okay, so this is why it's important to use the scientific method to test these types of things. You cannot just make baseless claims, right? That's why science is so important. Now we're going to move on to what is the difference between a fact and a theory. Well, as you test hypotheses, gather data, you may see that different researchers, because usually scientists in the same field talk to each other, may be conducting similar experiments and are finding the same results. Okay, so over time, with the same methodology being used, with the same experiment being conducted, similar test subjects, etc., similar results are being found. Eventually, it can be taken as a scientific fact. Okay. And that's the beauty of the scientific method. It's supposed to be repeated. It's supposed to be a self-checking process that anybody or any scientist in the same field could do. But it is important to know that a fact in science is the current understanding based on the experiments that have been done up to this point, meaning that up to this point in time, let's say 5 experiments have been done by 5 different people, but the same methodology has been used and it gave the same results, and all the same 5 scientists said this is a scientific fact, that is the fact at that moment. But let's say in 2 years, 2 different scientists test that original methodology, that original experiment, and get something else. Well, then the scientific fact may be changing, okay? So science is changing, is ever changing. That's the beauty of it, okay? We always keep open the possibility that new data will be generated and that change in our current understanding may show that past understandings or facts are false. Here are some excellent examples of former scientific facts that were eventually shown to be false. So they are now considered scientific beliefs, right? In the 1800s, many scientists believed that Earth and other planets were continually expanding in size over time. Now, more recent astronomical finds have shown that Earth has not undergone any significant change in size for the last 100 million years. Okay. Now, you can read these 2 other scientific beliefs that were thought to be fact. I'm not going to go into them, but now I want to talk about theory. And we start theory by talking about Louis Pasteur. He made many important scientific discoveries, including proving that organisms cannot spontaneously generate. That is really, really important. And so, a series of facts related to a central question that continue to be well supported over time can be combined together and called a scientific theory. Okay. The use of the word theory in science is different from how we commonly use the word. In our casual conversations with others, we often say we have a theory about things that are not supported by any data or results. But in science, the term theory is only used for very well supported hypotheses regarding explanations in the natural world. Okay, the theory of relativity. These theory is, yeah, for us very casual, right, in our everyday conversation, but that is not the case. So it's important to keep this in mind. That's it for this lesson, but we are going to continue on. So now that we've talked about the scientific method, lesson 2 for module 2 is what are the types of data and how can data be analyzed? We will discuss different types of data that can be collected from the testing of hypotheses and some ways that data can be analyzed. And there are 4 main types of research data based on how the data was collected: observational, experimental, simulation, and meta-analysis. Now, in the previous lesson, we only talked about observational and experimental, right, studies, but even from the data collected from observation and experimental, you can generate simulation data, and that's because we use highly advanced modeling techniques nowadays so that we can predict future outcomes, and that is data. Okay, and a meta-analysis data is data compiled from many studies to show a larger trend. We really see that in ecology because several scientists, ecologists, animal behaviorists seeing the same type of behavior or the same type of pattern with a set of animals, like let's say frogs, and then somebody compiles all of that data together, that would be meta-analysis data, okay? Or a literature review is meta-analysis data. Let's say you want to start an experiment on, let's keep it related to water, on rivers, right? And you want to understand how people interact with rivers. just in general. You look on a database that has several published studies, sociological studies on the public's relationships with rivers, okay, and get 500 articles. You start categorizing them and compiling them and kind of deciding what attributes each um, set of papers has. That is a meta-analysis data that you are compiling. So here, as an example, we have an algal bloom in British Columbia. Before we had the tap versus bottled water example, this is an algal bloom, which I like a little bit more. So there's a lot of different types of data that you can gather from the study of an algal bloom. So what could they be? Well, we can have observational data from the algal bloom itself related to the color or the thickness of algae in different locations, or what's the area coverage. Experimental, if we start performing experiments related to water quality and seeing how the algae behaves when added certain compounds, right? That would be altering variables. And the algae could be, right? So that's the second part. Simulation data to understand the structure of a protein produced by algae, or provide a model of how fertilizer levels could impact the growth of future blooms of algae based on what we're seeing in the present. And the meta-analysis compiled data could be that several smaller studies tested the impacts of chemicals like nitrogen or phosphorus, and if we could see that how that impacts the overall algae growth, if there's a trend available. Meta-analyses are becoming more common as data from smaller studies on a similar topic are combined and analyzed, and a statistical analysis is performed on the larger data set to see if there's a trend that might be seen that could not be gleaned from just looking at one or two studies. And there is also the types of data that can be collected in terms of quantitative or qualitative. So quantitative data comes from measuring things. And this is how most like natural scientists and physics, chemists, biologists, ecologists, atmospheric scientists, et cetera, collect their numbers. It's basically number-based information. You use graphs and charts, and then statistical methods to analyze data. In the next figure, what you will see is the level of arsenic in the drinking water supplied by the city of Ohio, and then and other contaminants, and then the amount allowed. So the amount detected and then the amount allowed. This is quantitative data. Now, qualitative data, sorry about that, does not involve things that can be easily measured, and it's data often gathered from observations, interviews, or questionnaire. It's usually text-based data. You see it in sociological, a lot in sociological studies. What you're looking at this example in figure 2.6 is qualitative data. In this case, examples of quotes from a survey on people's beliefs regarding the healthiness of bottled water, right? But how do we analyze this data? Well, despite the terms being used interchangeably, it is important to remember that data and statistics are not the same thing. Data are pieces of information that are produced from an experiment or observation. It can be quantitative or qualitative. Statistics is the analysis and interpretation of data. So you actually do statistics, okay? And data is what you kind of pull from and then conduct statistical analysis, okay? Statistics can be used to be able to quantify the uncertainty in data we have collected. For example, if you find that there are higher amounts of arsenic in bottled water compared to tap water, is the difference meaningful? Well, if you're interested in that analysis, it is often analyzed and presented in the following 3 ways: confidence intervals, a p-value, and a correlation coefficient. So this is a very basic overview of statistics that is commonly used in science. What are confidence intervals? Well, often when data is presented, the mean or average will be shown for a set of data, but you cannot tell from the average how close the values in this data set are to the mean, okay? So this is a great example to basically understand confidence intervals. There are 3 samples with values of 5, 5, and 5. And so 5 would have the mean of 5. A data set with 3 samples of 0, 5, and 10 would also have the same average, but there is a much wider variation in the second data set, right? Because the data sets are different. So the confidence interval represents the amount of variation in a data set. And so if you hear somebody, a scientist or an article say there is a 95% confidence interval, that's within the range of 95% of the values from the data will fall within that set, okay? So here we have several samples, okay? These are the amount of dissolved oxygen in New York Harbor. It provides an example of how the confidence intervals can be displayed using data on the dissolved oxygen levels in water taken at different times and locations from New York Harbor. Dissolved oxygen is an important predictor of aquatic health and is often depleted during algal blooms, okay? So let's look at the first one. 2012 to the top, okay? It was 808 samples taken. The mean was around 7.35. The 95% confidence lower interval reached 7.12. And the 95 upper confidence interval reached 7.59, okay? Let's compare it to the 2012 bottom. Here we can see that the mean is lower and that the lower confidence interval reaches 6.60. So in this portion of the water sample with 808 water samples, it has a lower dissolved oxygen than the 2012 top. This makes sense, right? Top and bottom are the surface and the bottom of the water column in the New York Harbor. We would expect that the surface, aka the top, would have more oxygen than the bottom, aka the sea, the harbor floor, right, of the water column at present, because dissolved oxygen will be closer to the atmosphere in higher quantities. Although it's not that much different, it can make a significant amount of impact because different fish and different animals and different organisms require different levels of oxygen. So if a fish that lives in the middle of the water column does not get enough oxygen, it could die, float to the top, and the decaying body, along with bacteria, can deplete oxygen further, like what we saw with eutrophication. Now we're going to look at p-values. So the p-value is a number that results from a statistical test that can be used to determine whether a set of data supports a hypothesis or not. The p-value is the likelihood that there is no difference between the data sets you are comparing. The lower the p-value is, the higher the chance that there is a significant difference between your data sets, okay? Typically, a p-value is to be below 0.05 for the comparison to be statistically significant, but the lower the value, the better. If you're comparing arsenic levels in bottled water and tap water, and you find a p-value of 0.2, that means there is a 20% chance that there is no real difference between the two data sets. However, a value of 0.01 means that there is only a 1% chance that there is no real difference, and therefore this would be considered statistically significant. So it's a little bit confusing, okay? But I'm going to try to explain it in more simple terms, okay? P-value is used to see if there is a difference, to see if there is a significant difference between data sets, okay? So let's say you have, let's keep using the arsenic level, right? So you have bottled water and tap water. If your p-value, if you want it to be statistically significant, usually you set your alpha value. That's kind of like the alpha value is the value that you use to compare your p-value to, right? And it can change. Here they usually use 5%, which is 0.05, because that's the standard for statistically significant. However, I've seen it be 0.01, and you definitely want it to be below that number in order for you to say, oh, okay, there is probably a statistically significant difference in these data sets, okay? So although they don't talk about the alpha value, it's important to know that you first set your alpha value, right? And then once you get the p-values, you would compare it to the alpha value. Now, if your p-value is above your alpha value, that means that there's no real difference, that there's no real change, that one does not significantly influence the other, and that's why you would not accept your hypothesis. You would fail to reject your hypothesis. Now, if your p-value is way below your alpha, that means that the percentage of difference between the data sets is considered to be like the difference between the two data sets is that there's only 1% chance of no real difference, right? Or less than whatever your alpha value is, then it would be considered statistically significant. So it's kind of like backwards, but once you understand p-values, it gets a lot easier to understand scientific papers because it's still the most commonly used test that we do in science, although it has been argued that we should switch over to a different way. Now, a correlation coefficient. This one is how we introduce data analysis and statistics to people. A correlation is a relationship between two things. A positive correlation means that as one goes up, so does the other. Okay, so we know that when the blades of a wind turbine increase their speed, the amount of electricity produced also increases, right? It's a positive correlation. A negative correlation means that as one thing goes up, the other goes down. We know that as the elevation increases, temperature will decrease. That's a negative correlation. And you can see here the graphs. So we have our variables, and the way that we calculate this is into the correlation coefficient, which is R. It describes the relationship between two variables being graphed. No correlation or correlation coefficient of 0 means that there's no relationship between two variables. A positive correlation means that one goes up, the other one also goes up. And then yet again, a negative correlation that means that as one may be increasing, the other one is decreasing. Now, what is causation? Because sometimes you might hear somebody say, correlation does not equal causation. Okay, well, causation is when one variable has a direct influence on the other. An example is carbon dioxide in the atmosphere increases, so does global temperatures increase. However, just because there's a correlation between two variables, it doesn't always mean that it's a causation. There are so many examples that can be graphed with an almost perfect correlation, yet they have nothing to do with each other. An example is arcade revenues and computer science doctorates awarded each year. There seems to be a correlation between the two, right? But no one thinks, because as let's look at it in the next graph. As arcade revenues go up, so does their arcade revenue goes up, so does computer science doctorates increase, right? So one might be thinking, oh, people that are very, very intelligent, computer science doctorates, love to play video games. That's why video games and arcades are doing so well, right? That's not necessarily true, okay? That we cannot say that a link between two factors is a causation. That requires a different scientific method and accurate analysis. So correlation can sometimes be used to promote falsehoods and claims meant to sway opinions or encourage people to buy products. So be careful out there with those types of weight loss drugs and other things that might be offered to you, because correlation does not equal causation. Always remember that. Now, we're going to finally finish off Module 2 with, can you think like a fact checker? So, continuing on is that we will discuss pseudoscience and how bias can influence the collection of scientific data. I really like this because we saw a lot of this during the pandemic, COVID-19. It seems that conspiracy theories fuel pseudoscience, and that really can influence people and dissuade them from understanding the scientific method. So, and an amazing example of pseudoscience to start off is phrenology. And this was started in the 1700s by a German physician, Franz Joseph Gall, who proposed that bumps on different regions of the skull were associated with specific personality traits. This concept later became known as phrenology. It became very popular in the early 1800s, and even the Queen of England, Queen Victoria, and her husband had their children's heads read by a phrenologist to assess their children's personalities. Despite the popularity, there was one thing missing from phrenology, specifically any studies of the concept that had used the scientific method. By the 1840s, the controlled scientific studies showed that it was regions of the brain itself that led to different personality traits and not the bumps on the skull. And because of that, phrenology is known as a pseudoscience. While there's so many different examples of pseudoscience, they often share some similar characteristics. Their claims cannot be tested, or they're so vague that it would be difficult to test with the scientific method, aka, remember, a question needs to be testable and falsifiable. Okay, if it can't, that's not a good question. A good research question. They often apply anecdotal evidence, something that only one person has experienced, to draw general conclusions, or they rely on celebrity testimonials to support the claims. Pseudoscience also often uses complex words and phrases to make it seem to be more scientific. Okay? Yes, science has some very complicated terminology, specifically medical science. But pseudoscience has manipulated that thought to create even more complex jargon that can be misconstrued as true. So please think of other examples of pseudoscience. I think one of my most favorites that everybody likes and knows is unfortunately astrology. Astrology is the thought that the placement of the earth on the day that you were born determines your personality traits. And although it seems that you can easily relate to a lot of the descriptions in your astrological chart, star chart, whatever, sometimes we may think that they are so vague or anecdotal that it could really be applied to anybody. Scientists have tried and tried again to prove if astrology is true, and it is simply not. So, some of you may get angry for me, and it is kind of fun to look up your zodiac sign and all that, but it is a pseudoscience, and should not be taken seriously. Can a bracelet improve your balance and agility? This was an interesting claim that a hologram bracelet could improve balance and agility. All the scientific studies that have been done with these bracelets have shown no improvement in any areas related to athletic performance. Um, Pseudoscience also usually doesn't allow its claims to be open to outside review, similar to a conspiracy theory. One of the hallmarks of the scientific method professionally is that its results are usually published in scientific journals. Okay, these are also referred to as primary sources as they contain details of the original research and results. The primary source, the original journal article, is often very detailed and technical, which can make it difficult for non scientists to read and understand. Now, reputable journals are different from other media in that the articles have undergone the process of peer review. This is a critical part of science in which the authors of a scientific paper have the details of their experiment design and results anonymously reviewed by other experts in their field. This is called peer review. The reviewers critique each part of the paper, suggesting changes that would improve the study design or the validity of the results. These suggestions are then taken to the original authors, and often these changes must be made before the paper is accepted for publication. The result is that an article established in such a journal has already been reviewed and approved by several other experts in that field. This means that the results can be trusted more than an article that has not undergone peer review. So, yet again, scientific journals. And you also have to look because now pseudoscientists are creating their own scientific journals. It is a very difficult and intense process to get published. Okay. I have been on several journal articles and it takes between 2 to 3 years, even after you've already completed the experience, to write it up, to submit it, and get it rejected about 2 to 3 times usually before it is completely ready to get fully published. Now, I like this process. It is difficult, but I will tell you that it's helpful to have reviewers in your field that are experts and that are not biased, right? So what these scientific journals do is they ask you to submit all of your affiliations with universities, academic institutions, professors, other scientists in the last 10 to 15 years, because they want to make sure that whoever they reach out to review your journal article will not be affiliated in any way, shape, or form with you, meaning that they will not have any bias for or against you. So that's really important. Remember, science is dry and straightforward. There is little room for emotions to be involved. So the peer review process of journals cuts that out. Now that you've learned about primary sources, well, newspapers and news websites are considered secondary sources. They summarize the findings of primary sources. But as explained in the previous slide, a lot of people, the general public, cannot understand sometimes the heavy scientific, especially in medical journals, the heavy scientific information presented in primary sources. So secondary sources may be the way to communicate that properly. And that's a whole new field called science communication. However, there are downsides, and that's some of the data may be presented out of context, and this could lead to misleading conclusions. So there's still problems with that. That's why it's good for scientists to become more engaging, more public entities so that they can figure out ways to communicate their science to the public, right? Because I know a lot of people who are just like, I don't want to listen to the science of what you're talking about. Just tell it to me straight. And I have to come up with a 3 to 4 sentence summary of what I've studied, of what I've implemented, right? And I have to make it easy for them to understand. And that's okay. So it's good for scientists to become science communicators. What is bias? I've already, mentioned it a little bit, but it is the preference for one idea over another, which can skew the results of a scientific experience. In some studies that were very commonly done in the past, an example was that males or only people over a certain age were included, right? And that would be a limitation that needs to be mentioned if the study will be published, because that does not represent the entire population. Studies often involving humans have a very large sample size in an attempt to minimize bias. The more people included in a study, the lower the chance that bias will influence the results. Just because of what I mentioned. If you want to show to the scientific community, your scientific peers, even just everybody, that this is going to influence everybody, you are not going to just test it on, one type of person. Okay. So all females, all predominantly Caucasian. You want a large sample size that mixes everyone, all ages, different ethnicities, and all both genders, right? So that's why this is very important. There are a lot of other types of biases. However, these are the major four. You can look them up in your book. It would be too complicated for me to go into depth, but please read that in your book. And now, how can you be a fact checker? Okay. As a citizen, as an educated person, you need to become a fact checker. You need to think like one and determine if something that you hear is scientifically valid or just pseudoscience. So, here are 4 questions that you can ask to sift from the valid and from the invalid. Where is the source of information, right? This is important. Does it come from a .com or a .edu? .edu usually signals academic institutions, post-secondary institutions, universities, etc. But also be careful because even a .edu could be funded by a .com. What do I mean by that? An academic institution may be receiving funding dollars from a company, from a religious organization, etc., and because of that, their source of information may be biased. Are there any peer-reviewed primary literature articles to support the claim? Yet again, I talked to you guys about looking into web-based science databases. So I like to use Web of Science, um, Google Scholar. Like you want to look and find not just 1 or 2 articles, but maybe 4, 5, 6, 7, above of peer-reviewed primary literature that supports the same claim, okay? Does the claim rely only on anecdotal evidence? We cannot trust what people say, unfortunately, because we all have our biases, our own opinions. So somebody telling you, I saw, if 5 people tell you, I saw a cat, I don't know, start typing in front of a computer, you might be like, well, 5 people said that they saw it. That's a good number. That's anecdotal evidence, okay? Even if it's 5 people, you need to make your own research. Is there any evidence of bias in the group that is making the claim? Yet again, this tied back to the first one, which I mentioned. Even .edus could be getting funded by a private religious public entity with a different agenda and could be inserting their biases in there. We're going to go back to Cleveland's municipal drinking water and the claims made by Fiji. There were several reasons the advertisements by Fiji could be considered an example of pseudoscience. 1, there was no data presented comparing Fiji water contaminant levels or any other measures of water quality. 2, the makers of Fiji water were biased in their advertisement because they were hoping to convince people to buy Fiji. And 3, the next time you hear about a product that claims or implies that it's healthier for you, remember to think like a fact checker and investigate before believing the claims are true. These are Module 2's critical thinking questions. They are really cool, really important. So look these over, keep them in mind. I think if you try to answer these, they will help you in the exam. And that's it for now. I'll see you guys in the next module.